A small beginning in a large universe. Sir Isaac Newton entered the world so quietly that no one could have guessed how loudly his ideas would later echo. He was born at Woolsthorpe Manor in Lincolnshire, England, on December 25, 1642, by the old calendar then used in England, or January 4, 1643, by the modern calendar. His father, also named Isaac Newton, had died before the child was born. The infant was small and fragile enough that his survival seemed uncertain. Yet from that precarious beginning came one of the most consequential minds in human history. Newton's early life was marked by distance and inwardness. When his mother, Hannah Ayscough Newton, remarried, he was left in the care of his grandmother for several years. The emotional effects of that separation are impossible to measure exactly, but the record of his later personality suggests a man who guarded himself fiercely and trusted slowly. Even so, there is something quietly hopeful in the picture. A child who had reason to feel alone learned to make companionship with questions, tools, and the world outside the window. He grew into a student more fascinated by mechanisms, drawings, sundials, and secret notebooks than by the ordinary rhythms of rural life. The young Newton built small devices, observed the wind, copied diagrams, and treated the world as a puzzle box waiting to be opened. This was not yet the Newton of universal gravitation. It was something more delicate, curiosity learning how to become patient, and patience learning how to become power. Woolsthorpe was not a grand capital of learning. It was a rural place of fields, stone walls, seasons, tools, weather, and sky. Yet those ordinary surroundings gave Newton a lifelong habit of looking carefully. Long before he explained the motion of planets, he had learned to notice shadows crossing a wall, wind pressing against a field, and light falling through a window. The universe was already speaking softly. Newton was learning to listen. What makes Newton's childhood compelling is not that it foretold everything. It did not. He was not born with a printed destiny in his hand. Instead, his youth shows how curiosity can gather strength in quiet corners. A farm, a window, a notebook, a patch of sky. In the right mind, these can become the beginning of a new way to understand nature. Cambridge and a discipline of questions. Newton arrived at Trinity College, Cambridge, in 1661. The university he entered still taught much of natural philosophy through Aristotle and scholastic tradition, but Europe was already alive with new methods and new doubts. Copernicus had displaced Earth from the center of the heavens. Galileo had used mathematics and experiment to describe motion. Descartes had insisted that nature might be understood through mechanism. Newton absorbed this inheritance with unusual intensity. He did not merely read books. He interrogated them. Cambridge gave him the old world, but it also gave him a place from which to push beyond it. The most important feature of his education was not obedience to a syllabus. It was the growing confidence that inherited explanations could be tested, revised, and sometimes replaced. In that confidence there was a bright, brave feeling, the sense that the mind, if disciplined enough, could meet nature face to face. His student notebooks reveal a restless intelligence moving beyond the curriculum. Under headings about philosophical questions, Newton recorded problems about matter, motion, light, perception, and the structure of the cosmos. The phrase could almost stand as a motto for his youth. He was not satisfied with inherited answers. He wanted causes, demonstrations, and relations that could be tested by reason. At Cambridge, Newton developed the habits that would define his greatest work: long concentration, suspicion of vague language, and a remarkable ability to connect physical intuition with mathematical form. He was not a polished public speaker or an easy networker. He was often private, intense, and competitive. But solitude was not emptiness for him. It was a laboratory, and in that laboratory, curiosity became disciplined inquiry. This period matters because Newton did not simply reject the past. He climbed through it. He studied the thinkers who came before him and then pressed against the limits of their explanations. His genius was not a lightning strike detached from history. It was a demanding conversation with history, carried out by a mind that wanted nature to answer in a stricter language. The Plague Years and the Private Revolution. In 1665, The Great Plague forced Cambridge to close, and Newton returned to Woolsthorpe. The interruption might have seemed like a pause in his education. In reality, it became one of the most astonishing periods of intellectual productivity ever associated with a single young scholar. During the months away from the university, Newton worked on problems that would later become central to calculus, optics, and gravitation. The famous apple story belongs to this phase of his life, though it has often been softened into legend. Newton did not suddenly discover gravity because a fruit struck him on the head. The more meaningful version is quieter and more powerful. He saw, or later remembered seeing, an apple fall, and he asked whether the same force that drew the apple downward might extend far beyond the tree, perhaps even to the moon. That question required a radical act of imagination. It joined the familiar and the cosmic. It suggested that the motions of everyday objects and heavenly bodies might obey one system. There is a lovely generosity in that idea. The universe did not need separate rules for the orchard and the heavens. The same order might be present in both, waiting for a mind patient enough to recognize it. Newton also developed what he called the method of fluxions, a way of reasoning about changing quantities that belongs to the history of calculus. He investigated infinite series and refined mathematical tools for motion, curvature, and rates of change. These were not merely clever tricks on paper. They were new instruments for thinking about a living, moving world. The plague years show Newton at his most mythic, but also his most human, a young man isolated by crisis, using forced retreat as an opportunity for fierce thought. The world outside was fearful and unstable. Inside his mind, new order was forming. That contrast gives the story a surprisingly positive charge. Even interruption in the right hands can become a doorway. Light split open. Newton's work on light reveals one of the clearest features of his genius. He could turn a simple experiment into a decisive argument. In a darkened room, he allowed a narrow beam of sunlight to pass through a prism. The light spread into a band of colors: red, orange, yellow, green, blue, indigo, and violet. Others had seen prisms make colors before, but Newton pursued the phenomenon with unusual care. He passed the colored rays through additional prisms and showed that each color bent by its own amount and could not be changed into another color merely by further refraction. That care matters. Newton was not content with a beautiful display. He wanted the experiment to answer a precise question. Beauty opened the door, but discipline made the discovery. From these experiments, Newton argued that white light is not pure in the old sense. It is a mixture of rays with different degrees of refrangibility. Color is not simply a modification caused by glass or shadow. It belongs to the rays themselves. This conclusion helped transform optics from a field of appearances into a field of measurable physical behavior. Newton's optical work also led him to design the reflecting telescope. Refracting telescopes suffered from colored fringes because lenses bent different colors by different amounts. Newton used a mirror instead, reducing chromatic distortion and demonstrating the practical power of his theory. His reflecting telescope, presented to the Royal Society, helped make his reputation. Optics also brought conflict. Robert Hooke criticized Newton's ideas, and Newton, sensitive to criticism and reluctant to publish, withdrew for a time from public debate. The episode exposed a recurring tension in his life. He craved certainty and recognition, but public science required argument, revision, and exposure. Even so, the prism experiments remain a model of rigor: a beam of light, a dark room, and reasoning sharp enough to split white into truth. The Principia and the Architecture of Motion. Newton's greatest public achievement appeared in 1687 under the Latin title Philosophiae Naturalis Principia Mathematica, usually called the Principia. It is one of the most important books ever written. In it, Newton set out 3 laws of motion and the law of universal gravitation, then used them to explain phenomena ranging from falling bodies to planetary orbits, tides, comets, and the shape of Earth. The Principia did not appear in isolation. Edmund Halley encouraged Newton, visited him, recognized the importance of his work, and helped arrange publication. Without Halley's persistence, Newton might have delayed or withheld parts of the book. That collaboration gives the story warmth. Even the most solitary genius sometimes needs someone else to knock on the door and say, "This matters." The first law states that a body remains at rest or moves uniformly in a straight line unless acted upon by an external force. The second connects force with change of motion, giving later physics one of its central mathematical frameworks. The third declares that for every action there is an equal and opposite reaction. These laws did not merely collect observations. They provided a structure in which motion could be analyzed across scales. Universal gravitation was even more astonishing. Newton proposed that every particle of matter attracts every other particle with a force that depends on their masses and decreases with the square of the distance between them. The same principle that could describe an apple falling could also describe the moon's orbit around Earth and the planets, paths around the sun. The book was difficult, compressed, and mathematically demanding. But its effect was enormous. It made the universe seem intelligible in a new way, not less mysterious, but more deeply ordered. This is one of Newton's most positive legacies. He did not flatten wonder. He gave wonder a framework sturdy enough to carry prediction, engineering, astronomy, and awe. Power, coins, and the public Newton. Newton is often imagined as a pure thinker, untouched by administration or politics, but the second half of his life complicates that picture. In 1696, he became Warden of the Royal Mint, and in 1699, he became Master of the Mint. These were not ceremonial posts for him. England's coinage was in crisis, threatened by clipping, counterfeiting, and the difficulties of recoinage. Newton approached the mint with the same severity he brought to mathematics. He studied the machinery and procedures of minting, tracked counterfeiters, gathered evidence, and pushed prosecutions. The work was practical, exacting, and at times harsh. Yet it also shows a public-minded side of Newton. He understood that a society depends on trust, and that trust often lives in small, measurable things. The man who had unified celestial and terrestrial mechanics also cared about the weight of coins, the reliability of currency, and the legal machinery of trust. Money, like motion, depended on standards. In a different register, Newton was still asking the same kind of question: what rules make order possible, and how can we know when those rules have been violated? Newton also served briefly in Parliament and became an increasingly public figure. In 1703, he was elected President of the Royal Society, a position he held until his death. In 1705, Queen Anne knighted him, making him Sir Isaac Newton. By then, Newton had become a national figure. Scientist, administrator, institution builder, and symbol of English intellectual power. Yet public Newton could be severe. As President of the Royal Society, he exercised authority forcefully and sometimes unforgivingly. His later years were marked by disputes over priority, reputation, and control. The same intensity that made him a great investigator could make him a formidable rival. His life reminds us that genius does not erase temperament. It magnifies it, the difficult human being behind the monument. Newton's reputation can become so monumental that it hides the complicated person underneath. He was brilliant, disciplined, and capable of extraordinary intellectual courage, but he was also secretive, anxious about criticism, and often combative. To see him clearly is not to admire him less. It is to admire the achievement with better eyesight, and to remember that great work can come from difficult human material. His disputes with Robert Hooke became famous. With Hooke, Newton clashed over optics, and later over ideas connected to gravitation. Hooke was himself an important experimental philosopher, energetic and inventive. The conflict was not a simple story of right and wrong personalities. It was also a reminder that science advances through friction, and that even friction can sharpen ideas when the evidence survives it. With Gottfried Wilhelm Leibniz, the argument centered on the invention of calculus. Today, historians generally recognize that Newton and Leibniz developed calculus independently, using different notations and styles. At the time, however, the controversy became bitter, nationalistic, and personally damaging. It is one of the great cautionary tales of intellectual pride. Discovery is bright, but ownership can cast a long shadow. Newton also devoted immense effort to subjects that do not fit the modern image of the scientist. He studied alchemy, chronology, biblical prophecy, and theology. He held religious views that would have been dangerous to state openly in his world. To modern eyes, these interests can seem separate from his science, but for Newton they belong to a larger search for hidden order. This does not mean we should romanticize every part of him. Newton could be harsh. He could use institutional power to defend his reputation. He could hold grudges with remarkable stamina. But acknowledging those traits makes his achievements more human, not less impressive. The Principia was not written by an abstract statue named Genius. It was written by a difficult, lonely, ambitious, devout, suspicious, and relentless person. Newton's long shadow. Newton died in 1727 and was buried in Westminster Abbey, an honor that signaled how completely he had entered public memory. By then, Newtonian science had become more than a set of discoveries. It had become a vision of what knowledge could be: mathematical, predictive, universal, and disciplined by evidence. For generations, to explain something scientifically often meant to explain it in a Newtonian spirit. Burial in Westminster Abbey placed Newton among the figures a nation chooses to remember. But his memorial was larger than stone. It lived in classrooms, observatories, shipyards, workshops, and the imaginations of people who believed that the world could be understood. His life helped make disciplined curiosity feel honorable, even heroic, and that is a legacy with real human warmth. His influence reached far beyond physics. Engineers, astronomers, navigators, philosophers, and political thinkers drew confidence from the idea that nature followed discoverable laws. The Enlightenment took Newton as proof that reason could uncover order where previous ages had seen mystery or authority. That confidence was not naive optimism. At its best, it was courage joined to method. His work helped build the intellectual foundations for modern technology, from celestial mechanics and ballistics to machines, bridges, engines, satellites, and spacecraft. Newton was not the final word, but he gave later generations a working language of motion. Every bridge calculation, every orbital correction, every launch trajectory carries a trace of that language. In the 20th century, Einstein's theory of relativity revised the Newtonian account of gravity, space, and time. Quantum mechanics transformed the understanding of matter and measurement. Yet these later revolutions did not simply discard Newton. They show the domain in which his laws are extraordinarily accurate, and the conditions under which deeper theories are needed. That is how living knowledge grows, not by humiliating the past, but by learning where it still works and where it must open. Perhaps Newton's deepest legacy is a habit of mind. He showed that the universe could be approached with humility and boldness at once. Humility before observation, boldness and mathematical imagination. Newton once wrote that if he had seen further, it was by standing on the shoulders of giants. The line endures because it contains a truth larger than Newton himself. Knowledge is cumulative. Even the greatest minds inherit a world of questions. Newton's greatness was that he gave those questions a form powerful enough to guide centuries.